Alright, so now we know our four gas laws. We're going to try to use these four gas laws to solve different types of problems when they are written as an equation. So we're going to have to use the gas laws as an equation to solve different types of problems. And I have three examples for you. First, I just want to point out that here are our gas laws, all of them, and they're all written out as an equation. You can go back to your notes to refer to which gas law each one of these represents. Here in the red is the standard temperature and pressure, so 0 degrees Celsius and 1 atmosphere. And then also the conversion for Celsius into Kelvin. The reason I put this here is that all the temperature always has to be in Kelvin. So if they give you a temperature in Celsius, you have to convert that into Kelvin. That's the only conversion that we'll ever have to do with these gas laws is Celsius into Kelvin, and then we can actually solve our problem. Okay, so let's look at our first problem here. Our first problem says what would be the new pressure if 210 milliliters of gas at standard pressure is compressed to a volume of 175 milliliters, and that T, the temperature, is constant. Well, I have this little box here to help you kind of set up your problem, and I want to just kind of go through what to do with this box. So the P represents pressure, T, temperature, and V for the volume, which you all should know. The initial is the before, final is the after, and then the effect is the pressure going up, down, what's happening to the pressure, the temperature, and the volume. Are they increasing or decreasing? And we'll just put an arrow to indicate this. So for the initial, we're going to say that's the 1. So in this case here we have V1. That's the initial volume. The finals are going to be the ones with the 2's. So you can see here with P2. That would be the final pressure. The effect, again, we're going to indicate with an arrow. Did the pressure go up or down? Did the temperature go up or down, and so forth. We want to know what is the effect. Did it go up or did it go down? And we can refer to our gas laws to fill out this effect. So let's look at this problem. Let me clear all this stuff off for you. Okay, so in the first sentence it tells us what we're looking for here in this problem. It says, what would be the new pressure? New pressure. So the new pressure is going to be the final pressure, the after. That's what we're looking for, the new pressure. Then it says, if you take 210 milliliters of gas at standard pressure and compress it to a volume of 175 milliliters. So what we should realize is the 210 is a volume. Now we have to know, is it our initial volume or our final volume? If we read the question, we could figure out that that is our initial volume, 210 milliliters. Then it says standard pressure. Well, what does that mean? Well, if we go back down here to standard temperature and pressure, we know that the standard pressure is 1. So that's going to be 1 atm. That's our standard pressure. Then we have our last little bit of information here, 175 milliliters. We know that our volume, and that's going to be the final volume, 175 milliliters. This little bit of information is very helpful. Our temperature is going to remain constant, so we can just put a big X through that. We don't need to fill out that at all because it's going to remain constant, so none of that's going to change. So we don't have to worry about the temperature, which is good. Now let's fill out our effect box. So the volume went down, so I'm just going to put an arrow here, down, so the volume went down. And we want to see what is the effect on the pressure. Well, if we look at our gas law notes, we should know that this is an inverse relationship, so if the volume goes down, that means the pressure should have gone up. So our answer should be something more than 1 atmosphere. All right, so now we have to figure out which one of these laws do we want to use. And we want to use the one that has the P and the V. The T does not matter. So this has P and V, but it also has N, R, and T, which we're not concerned about. This also has P and V, but it also has T, which we're not concerned about, so we don't need that one. This has P, but there's no V. We don't need that one. This has V, but no P. We don't need that one. It's this one here at the top. So this is the one that we want to use. The P1 times V1 equals P2 times V2. This is what we want to use. So now we just have to just plug in our different values. So we want the value for P1. Here's P, remember, is our initial. So we have 1 atmosphere times V1. Here's V, our initial, those are our ones, right? So it's 210 milliliters. And that's going to equal our P2. Our P2 is our question, so we're just going to leave it as P2. We don't know what that is. That's what we're looking for. Times the volume, V2, our final volume. Remember, the final is our 2's. So that's 175 milliliters. All right, so I have my calculator, and now I want to solve for P2. This is just an algebra question now. So I have 1 times 210. I don't need a calculator for that. We can do that in our head. That's just 210. That's going to equal P2 times the 175. Now, to undo this multiplication, we're going to have to divide both sides by 175. So I divide this side by 175. I'm going to divide this side by 175. When I do that, these cancel, become 1. So now I'm left with this P2, which is what I want to know. And that's going to equal our 210 divided by 175 equals 1.2. Remember what unit we're in, right here, atmosphere. It's ATM. Okay, so moving on to our new problem here. Again, I'm going to move through this one a little quicker. Remember, you can rewatch this video as many times as you need, and just go to the examples and just rewatch the examples as many times as you like. So in this example, we have a volume, a sample of gas that occupies 250 milliliters at 15 degrees Celsius. And it says, what is the volume when the temperature is increased to 35 degrees Celsius? The first thing that I want you to realize is that we cannot use Celsius. Temperature has to be in Kelvin. So that's the first thing that I want to do, is just go ahead and convert those. Then I don't have to worry about it. So Kelvin equals our degrees Celsius plus 273. So our Kelvin here equals 15 degrees plus 273. So you don't need a calculator for this, but I'll just go ahead and show you on the calculator here. We have 273 plus 15 equals, and I have 288 Kelvin equals our 15 degrees Celsius. So instead of 15 degrees Celsius, I want 288 Kelvin. All right. Let's go ahead and convert the other one. Kelvin equals our 35 degrees Celsius plus our 273. Again, don't need a calculator for it, but I'll show you on the calculator. 273 plus 35 equals, we get 308 Kelvin equals 35 degrees Celsius. So we don't want this anymore. We have 308 Kelvin here. Great. All right, so let's move on to figuring out what variable is what. First, our question, it says, what is its volume when this other thing happens? So that means that it's going to be our final volume, our V2. That's what we're looking for. We have an initial volume here, 250 milliliters. We have an initial temperature, 288 Kelvin, and we have a final temperature, 308 Kelvin. Again, our pressure is constant, so we can just draw a big X through that. So in this case, our temperature is going up, and if the temperature goes up, if we look at our gas laws, we should know that the volume should also go up. So that's what we should see. So let's look at what law or what equation do we want to use. We want the one with V and T. Well, that's this one. So V1 times T, so we have V1 times T2 equals V2 times T1. And again, this is just algebra. We're just plugging in everything that we have. So remember, these are our ones, these are our twos. V1, 250 times our T2, 308, is equal to V1, or excuse me, V2, which is our question here. So we're just writing our question, times T1, which is here, 288. So just real quick, we can do this with our calculator here. 250 times 308 equals, we get 77,000 is equal to our V2 times 288. Now to get rid of this multiplication, we have to divide 288 here. That cancels. Divide this by 288. So in our calculator, we already have the 77,000 divided by 288 equals. So our new volume here is going to be 267.4. And that's milliliters. We keep the same unit, and it went up, so it matched what our effect should be. To keep this video short, I'm going to do the other examples in another video for you. So we're going to end the video here, and I will see you in class.